All right. So today we want to talk about the topics that are covered in chapter 3, which has to do with basic statistics or descriptive statistics. In particular, we want to talk about what we call measures of location and measures of variability. So some of those things that I'm pretty sure that you're familiar with from high school, such as mean, median, and mode. And then perhaps measures of variability you may not be as familiar with. So we will kind of go through the chapter in two sections. The first part, which we'll deal with, is the measures of location, and the second part will be the measures of variability. All right. So under chapter 3, those of you who want to follow along, you could kind of use your ebook, chapter 3. But I'm going to just go through, first of all, a couple of slides, the basic concepts, to review that. As I mentioned to you, the approach is that you watch the videos before coming, I review it, and then I work up a couple of problems, all right? So let's just do our review very quickly. So what are measures of location? Measures of location allow us to, in statistics, because the whole idea behind statistics is about collecting data in samples and then using the sample data to learn about the population. It would be nice to be able to describe the sample. If we can describe that sample, then we are also in a position to be able to at least attempt to describe the population, right? Which is where the data actually came from. So that's the idea behind the concept of being able to describe sample data. And so when we talk about measures of location, essentially what we're talking about is where in a distribution, when I say distribution, a collection of values, how are the numbers positioned relative to each other, all right? So location. So when we say the mean, the average of all of those numbers, that is what we call a measure of central tendency. That means most of the values should be somewhere around the average. If we talk about the median, that's a location as well, because that is sort of a middle number in our data that divides it into two equal parts. When we talk about things like the mode has to do with which numbers occur most frequently in our data, all right? So we're trying to find ways to describe our data so that it makes sense to somebody who's actually reviewing the data that we've actually collected. So let's go through some of the different types of measures. So some of the measures of location include the mean, the median, the mode, the percentiles, and quartiles. So the mean is fairly straightforward. We know that another word for the mean is the average. And so we're talking about the sum of all of the values divided by the number of values that we have. So if you've done 3 exams and you have an 80, a 90, and a 100, the average of those 3 exams would be 90, because the 80, 90, and 100 adds up to 270 points. When you divide it by 3, you will end up getting an average of 90%. So simply put, the mean, or the arithmetic mean, is just the sum of all of the values we have in the sample divided by the sample size itself. And we will demonstrate that a little bit later. The median, what it does is that it actually takes our distribution or our data and divides it into 2 equal parts, so that half of the values are below the median and half of the values are above the median. So if I do this, let's see here. All right. So, bear with me for a second. I'm just going to try to move this somewhere where I can see better. Here we go. All right. So in this case, we are looking at, if I took a set of numbers, just a set of random numbers, right? Let's just say I have the numbers 3, 4, 6, 9, 15, 21, 28. So I happen to have these numbers right here. So what is the mean? What's the mean? The mean, we've already talked about, is just the sum of all of these values. And I denote that by the sum of the x's, and I divide it by the sample size. That is my average. If it is a sample that I'm dealing with, it would be a sample average x bar. If it is a population, we denote it by sigma, and it would be the sum of the x's. But notice I would put capital N, where capital N represents the population, and then this N represents sample, all right? For the median now, the median divides the data into two equal parts. So the median has 50% above of the values above and 50% below. So for us to be able to identify the median, one thing we have to do is to arrange the data in ascending order or descending order. In this case, I've already set it up so that it's ascending 3, 4, 6, 9, 15, 21, 28. So the median would be the middle value. 1, 2, 3, 4, 5, 6, 7. We have 7 numbers. So the middle value is the 4th number. All right? So middle value is a 4th number. And so that would be 9 in this case. So that would be my median. But we do have a process or procedure for calculating that. The median, essentially, we'll calculate it, and if when we go through the notes, you will see it. But essentially, if we have an odd number of values, then it's just a middle number. If we have an even number of values, so say instead of 7, I had 8 numbers, then the median would be between the 4th and 5th numbers. So let me just demonstrate what I mean by that. If I made that 32, and let's erase this little section right here. So if I have this now, I have 8 numbers. 1, 2, 3, 4, 5, 6, 7, 8. So where's the midpoint? Well, if I want to get half of the numbers above and half below, that means I want 4 numbers be above and 4 numbers below. So my median would have to be in the middle of those 2 numbers. And if I want to put a number in the middle of those 2, it means I must average the 9 and the 15. So 9 plus 15 gives us 24 over 2 is 12. So we would use 12 as a median. All right, we would use 12 as the median in this case. So median is a middle value. If we have an even set of numbers, we take the average of the 2 middle numbers, 4 and 5 in this case. But if we have an odd number for our sample size, we just take that middle value, and that gives us the median. And we could describe the data by saying, for example, 50% of the values are less than 9 or less. 50% of them are 15 or more, whatever this data represents. So that's kind of useful. All right. Let's go back to our notes. If you have questions, please feel free to ask. We just did a quick review. So that's the mean and the median. What is the mode? The mode basically is the number in the distribution that has the highest frequency. Sometimes we could have more than one mode, so we call it multimodal. And so if a number occurs fairly frequently, then we have that number as the mode. In the data I just showed you a while ago, I had a unique number. There was no numbers that were repeated. So as a result, that distribution has no mode. All the values have an equal frequency. But by definition, the mode is the one with the highest frequency. Let's go through some of the slides that just kind of reinforces the definition. So I think the mean is one of the most common measures of location. We just average all of the data. If it's a sample, we use X bar. If it is a population, we use mu. And so it just takes all of the values in the sample, add them up, and divide by the number of values that we have to get the average. So you can see that here in the formula, where we sum all of the values, divide by n if it's sample, but if it's a population, we will replace it by capital N to do that. We have an example here given to us, and in that example, we have how many values? We have 70 apartments who randomly sampled in a college town. Monthly rents are as follows. So that college town could be Halifax, for example. You have 70 values. If you want to find the average rent, then we simply divide the sum of the 70 numbers by 70. What did we get for an average? Oops. We got the sum total of all the values will be 41,356 divided by 70. We have $590.80. So the average of the rents is $590.80. Cool.
Yeah, excuse me, Dr. Miller, are we supposed to see a black screen now, or are you sure?
Oh, let me see. Oh, it says pause. Okay, hang on a second. It shouldn't be pause. Bring my shared window to the front. Are you seeing anything? Not yet? Okay, let me try that again. How about that?
Okay, that's good.
Better now?
Yeah.
Okay, great, thanks. So the median is, as I mentioned already, is the sort of middle value, and it divides it into two equal parts, and there's an example here given to us. So if we have an odd number of observations, 7 in this case, we arrange everything in ascending order, and we simply take the middle value. But then if we have an even set of numbers, then we will take the midpoint. So in this case, we have these 1, 2, 3, 4, 8 values. We arrange them in ascending order, and then we take the average of the two middle values. So in this case, we are actually putting a value, placing a value in the middle and saying, okay, we'll use that as our median, and then 50% of the values will be above that, 50% of them will be below that value right there. So that's your median. Since we have 70 numbers in this example, where we're looking at rents, so that's an even number. So we will be looking for the average of the two middle numbers. If I divide 70 by 2, that means I have 35 numbers would be in one half, and the 35 numbers in the other half, which means that I must put a value between the 35th number and the 36th number, so that way I could have 35 numbers above and 35 below. So I'm averaging the 35th number and the 36th number, in which case it is just 575, all right? We won't deal much with the trimmed mean, but it's just that sometimes you have some extreme values in a data set, and if you delete a percentage of the smallest and largest numbers, you could actually trim the mean. You don't want extreme values to bias your calculations. So just to kind of explain to you what a trim mean is, it's just that you trim the data by taking out the extremes and then calculating the mean. So for an example, 5% trim mean is obtained by removing the smallest 5% values and the largest 5% values, and then computing the mean of the remaining values. So we won't do that too much. The mode, as I mentioned, the mode really is the value that occurs most frequently. So we simply need to take the data, the distribution, count the values that are the frequency, show the frequency of all of the values, and the one with the highest frequency is the mode. Now it is possible to have more than one mode in a distribution. You could have bimodal, which means that you have two, multimodal, which means you have more than two. If you have three, you could even call it trimodal. But then again, this is just ways of describing the data for us, okay? And in this example, with the rents, we see that $550 seem to be fairly common. We have how many values for that? 1, 2, 3, 4, 5, 6, 7 homes. 7 homes had rents of $550. So that appears to be the mode. We see 4 of them here with 400. We see 4 with 600. But and even 575, you have 3 of them here. But that's the one that's most, have the highest frequency, so that is our mode in this case. In some cases, we do a weighted mean. Let me just kind of give you a sense of that. Let's say if we wanted to get the average of a class, and we had, say for example, a breakdown of the number of students that got A's, number of students that got B's, number of students that got C's. If we wanted to compute what the average was for that class, if we knew what an A represented in terms of a mark, a B represented in terms of a mark, and a C, then we could actually calculate that. What happened is that the number of students who actually got those marks becomes the weight, and then the marks themselves, A, B, and C, becomes the X value. So let me show you what I mean by that. I'm going to have to do a new share. Okay. Right. So say, for example, I had grades and number of students. So if I say A, B, and C. So say, for example, I have 30 students who got an A, 50 students who got a B, 20 students who got a C. So let's say an A represents 90%, a B represents 80%, and a C represents 70%. If I wanted to determine the average for that class, those values right here would be my marks, which would be my Xi's, and the values right here would be my Wi's. So my average grade would be the sum of the weights times their corresponding value divided by the sum of the weights. So in that case, I would have to take the 90. In other words, 30 people had a 90. So if I multiply the 90 by 30, I'm adding up, essentially I'm adding up the total number of marks. So that times 30 plus 80 times 50, because 50 people had 80s, plus 70 times 20. So that's what I would actually end up adding all up. That will be my sum of my Wi times my Xi. And then how many people do I have in all? I have 100 students in this case. When I add this up, the weights over here, it basically says I have 100 students. So this is kind of how I would go about calculating that weighted average. I take the value of X and multiply it by its corresponding weight, add them all up together and divide it by the sum of the weights, all right? So that is how I would calculate a weighted average. That could be also to salaries, for example. So say if we have a number of workers in 3 salary categories. So let's say we have 20 workers making $30 an hour, 10 workers making $20 an hour, and see, another 20 workers making $15 an hour. If I want to find the average hourly rate that I'm paying for this group, then this would be my XIs, and that would be the weights. The weights would be the number of people actually working for that amount of money. The XIs would be the actual amount that they earn. So it would be 20 by 30 plus 20 by 10 plus 15 by 20, which is what, 600 plus 200, that's 800 plus 300 divided by 50. So that's 800 and 1100 over 50, 1100 over 50. So 5 into 110 is 52. Is it 52? Did I get this right? I don't think I did this correctly. 3 2 is 600. 200. And 2 by 15 is 30. 300, yeah. Oh, I see what happened. Okay, I'm making a mistake here. Sorry. That's fine. So 5 into 11 is 2. 5 into 10 is 2. So $22. That's the average hourly rate for that group. $22 an hour. All right? Okay. I'm hearing some things dinging here. Let me see if anybody has any queries in the chat. So let me just take a look at the chat room and see if there are any questions. Nope, no questions right now. That's good. Okay, so that's the weighted average. Let's get back to our PowerPoint. This is what I'm getting back to. Okay. So we see a similar example with wages. So that's the wages per hour, total number of hours. We could actually calculate the average wage per hour. And we would have our WI times XI, which would be this value right here, divided by the sum of the weights, which is the number of hours, total number of hours. And we get an average weight of $20, sorry, an average rate of $20.05. Okay. We don't really cover the geometric mean, but essentially it's the end fruit of the product of n numbers. And that is kind of difficult to really get a feel for that. It's used in things like population growth, looking at population growth. A lot of economic data try to look at the geometric mean as opposed to looking at the arithmetic mean. So it's useful when you're looking at the rate of change over several successive periods, quarters, and so on. But we won't focus on the geometric mean. So I don't think you'll have any questions in the assignment that deals with geometric mean. But essentially, we take if we have n values, we multiply them by each other and take the n fruit, and that gives us the geometric average. So if we have 2 numbers, we multiply it by each other, we take the square root. If we have 3 numbers, we multiply them by each other and take the cube root. If you have 4 numbers, and so on. All right. So that's the basic premise of that. Let's talk about percentiles and quartiles. So in addition to looking at the mean, the median, and the mode, sometimes we want to look at the data in terms of percentiles to describe it. So we'll say, what is the top 10%? So if I took grades on a final exam and I was to say, what marks did the top 10% get? That's like asking for the 90th percentile and above. If I said, what grades or what marks did the bottom 10% get, or the bottom 25%, then I'm looking for the 25th percentile. And if I know what that 25th percentile is, I could say 25% of the students got a mark of this amount or below, and so on. So percentiles are also useful in describing data, all right? To compute the percentile, we need to find its location, because remember, these are measures of location. So if I'm looking for the 80th percentile, what we do is we take 80% of the sample size n plus 1. We kind of we add that 1, so that because the way the distribution is, we want to be able to get n spaces in between the numbers. So we have to add an additional number so that we could get n spaces. If I have two numbers, right, and I want 2 spaces in between the numbers, I have to add a third number so that I have 2 spaces. So that if I have x1 and x2, there's only 1 space between those two. But if I wanted 2 spaces, as 2 numbers, 2 spaces, I have to add a third number so that an additional value, so that way I could get that second space. So we add this 1 as a way of allowing us to be able to compute a slightly more accurate location of the percentile that we want. So let's look at an example of that. We have 70 values. If we wanted the 56th percentile, then what we would have to take is, the 80th percentile, we would take 80% of 70 plus 1. 80% of 70 plus 1. So 80 times 70, 56. But then we have one more value right here. So that gives us a 0.8, so 56.8. So in essence, what we're going to do is we are going to find that 80th percentile by taking the 56 value, and that 56 value is the 635, which is here, and then we take 80%, 0.8, 80% of the difference between those two. You see, if it was 57, if we think about 57, that's the 57th number, that's the 56th number. The space in between here, we're traveling between 56 and 57. So that 0.8 represents 80% of the way in between those two, 80%. If it represents 80%, how do I express that? I must then take the difference between those two numbers and calculate 80% of it. When I take that 80% of those two numbers, the difference between them, and I add it to that one, that would be 56, location 56, but the 0.8 location is somewhere up here, 80% of that distance. And so that gives me 80th percentile as $646.20. All right? So that whole process right here, this piece, we refer to that as interpolation. We are there's extrapolation where you are going beyond something. Interpolation is when you are within. So interpolation is because we are within those two numbers. If I was extrapolating, I would go beyond those two numbers. So 80% of the way here is what I'm looking at. Let's just, if it was, say, 70th percentile. So the 70th percentile would give me 7 sevens of 49, the 49.7. That 0.7 would basically be, would mean that I have to go and find the 49th value and go 70% of the distance between the 49th and 50th value. Kind of what we'd end up doing. So that's 56, 55, 54, 53, 52, 51, 50, 49. So in between here, this is 49, this is 50. So if I say 49.7, That's the 49 value plus 70% of the difference. Well, the difference is 10. So 70% of 10 is 7. So that means that the 70th percentile would be 607. That would be the 70th percentile. All right? So I'm actually going to demonstrate that a little bit more a little bit later. So quartiles are just like percentiles. So instead of using, say, a quarter of n plus 1, we could just take 25%. We could find a 25th percentile, second quartile, 50th percentile, third quartile, 75th percentile. So since we know how to do percentiles, calculating quartiles are simple, because then we just do the 25th, 50th, and 75th percentile. But alternatively, we can write the quartiles as, for example, the first quartile would be 1 over 4 times n plus 1. That's the location of that. But what is 1 over 4? 1 over 4 is the same as 25 over 100, right? 50th percentile, 1 over 2, the location is 1 over 2 times n plus 1. But what is it? What is 1 over 2? 50 over 100. So we don't really need to express it in that fashion where we say quartiles, first quartile, 1 over 4, 2 over 4, 3 over 4, because we already know how to do percentiles. So let's just use our knowledge of percentiles to solve that problem. All right? So in terms of quartiles, if we wanted the third quartile, this is an example looking at the third quartile, so that's the same as the 75th percentile. We multiply 75 over 100 times 70.1 to give us 53.25, which means it is the 53rd number plus 25% of the distance or the difference between the 23rd number and the 53rd number and the 54th number. 53rd and 54th. Well, there's no difference between those two, so 25% of no difference is no difference. So therefore, our number will also be 625. All right? So that's quartiles. Let's see if there's anything else. So that's it. That is the end of that particular chapter. So let me just do an additional problem for you to demonstrate some of the same things that we just looked at. Okay? So here is some data, and those values right here represents the amount of time science teachers spend preparing in a week for their classes, and that's the amount of time English teachers prepare for classes in a week. Let me just equalize that so everyone can see it. Okay, and so we could actually do a comparison between those two things. For example, we could compare their means. So if you want to take this data down, you certainly can. It comes out of chapter 3 in your textbook. The exact number, let me see. I'm not sure if the number is exactly the same, but it's chapter 3. And that question was question 11. But that's in the previous edition of the text. I didn't change the numbers for my notes, but you could actually find it. It says, according to the National Education Association, teachers generally spend more than 40 hours a week working on instructional duties, right? The following data shows the number of hours worked per week for a sample of 13 high school science teachers and 11 high school English teachers. And so we have the values right there. So we could calculate the mean, median, and mode for this data. Let's just look at science teachers, for example. Science teachers. If we're going to do this for the science teachers, first thing we have to do is to order the values. Now, first of all, let me just, here's what I'm going to do. I'm going to order these values, make my life easier. Because I have this in Excel, I'm just going to sort. I'm going to sort the science. I'm going to just work with science for now. So data, I'm going to sort, and I'm going to sort science, smallest to largest. So that's all cool. There we go. That's weird. Okay, that's fine. So I've sorted the values. I'm just going to write it down on my iPad for a second because I will switch to my iPad. Give me a second. So science. And then the number of hours, so we have 49, 52. So you guys could be writing that data down if you want to. 53, 54, 54, 54, 54, 54. There, 1, 2, 3, 4. 5 values of 54. 55, 56, 58. 55, 56, 58, 61. All right? So we're going to for science teachers. Let me switch screen now so that you could see what I'm about to do. So here's the data for the number of hours. So hours of prep. So you can take that down. So if I want the mean, sample mean, it's just simply the sum of the x's divided by n. I just need to add up all of those values. It adds up to 707. And then I have 13 values. If I take the average of that, I get 54.38. So science teachers spend on average 54.38 hours. So you could repeat that with the English teachers just to find out what they spend. So that's the mean. Median. So the median is the middle number. How many numbers do we have in all? 13. So what's the middle of 13? It should be number 7. Let's see what. So we want the middle number. A half. The location would be a half times m plus 1, which is a half of 13 plus 1, which is 14, which is 7. So a half of 14 is 7. So therefore x7, the 7th number, if I look at my data, so that's 1, 2, 3, 4, 5, 6, 7. That's my 7th number right here. So my median is 54. So we see my average was 54.38. My median is also 54. And then the mode. By definition, the mode is the one that occurs the most frequent. Well, that was the 54. You have 5 values of that. So mode is 54. Right? Frequency is 5. So that is our mode right here. Excellent. Mean, median, mode. Now quartiles. If you wanted quartiles or percentiles, let's look at percentiles. So let's take the 80th percentile. So the 80th percentile, we have only 13 values. So it would be 80 over 100 times 13 plus 1 would be our location, the location of that percentile. So it is 80 over 100 times 14. So that's 0.8 times 14. The calculator, 1 second, equal 0.8 times, I should be able to do that mentally, 14 is 11.2. All right, 11.2. So $11.2. So what does that mean? It means that I gotta look for the 11th number, but then go 20% higher than that 11th number. So I need to do some interpolation because I didn't get a whole number. So 11, so that's 7, 8, 7, 8, 9, 10, 11. That's strange. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I must be missing a number. 54, 55, 56, 58, 49, 52, 53. Well, I'm missing a 53. Aha. But it does not change my answer, because it just means that my 7th number is here as opposed to here. So it does not change. And the mode is still 54. If I made a mistake, sorry about that. In terms of my numbering, I missed a 53 in the middle here. And so as a result, my counting was off. Okay, so I'm looking for 11.2, so that's number 1, number 2, number 3, number 4, number 5, 6, 7, 8, 9, 10, 11. So that's my 11th number. And 0.2 would be between that 56 and that 58. So that means that I have to go 20% of the distance between 56 and 58. Well, what's the distance between 56 and 58? 2. So I did 20% of 2. 2 2s are 4. So that would just be 20% of 2 is basically 0.4. So that means I would have to add that 0.4 to 56. So let me show you how I do that. So since my location is 11.2, I will take my L 80%, L80. We already, sorry, that's L80 is 11.2. So therefore my X, my 80th percentile would be X11 plus 20% of the difference between X12 and X11. That's interpolation. All right? So, but what is X11? It is 56 plus 0.2 times 58 minus 56. And that gives us what we're looking for, which is essentially 56.4. So that is the 80th percentile. That's it. That's percentiles. Okay? And so we're not doing weighted averages in this example, but I've already demonstrated that. We have percentiles, we could do quartiles. In that case, we would just change it from 80% to 75% for the third quartile, 50% for the second quartile, and 25% for the third quartile, for the first quartile. So if you understand how to do percentiles, you understand how to do quartiles as well. All right? So that brings us to the first part, which is measures of location. And so now we want to go to measures of variability. But before I go to that, let me see if you have any questions for me. Chat. No, there are no questions. Okay, good. Everybody's hearing me well? All right, let's then go to the second part of that, which is measures of variability. So we want measures of variability, share the screen. There you go. So this is 3B, measures of variability. So when we talk about measures of variability, what are we referring to in this case? What are we referring to? So measures of variability are different from measures of location. Location takes our data and it sort of puts values in it and helps us describe where the numbers are. Measures of variability, on the other hand, tells us more about how the numbers are spread out. Are they very variable? So for example, if I have 5 numbers, 1, 2, 2, 2, 3, 4, maybe that's not very spread out. But if I have numbers like 1, 7, 13, 54, 95, those numbers are very spread out. So there's a lot more variability in that second data set than the first one. And that's actually important for us to understand variability, because in some cases, variability indicates instability. So for example, stock prices, if the price of a stock is varying quite a bit, then it's volatile. If it's volatile, you may not want to invest in that stock because one minute you have great value, another minute you have very low value. So in that case, I would say when it comes to stock values, we want stability. If I am looking at great performance and I see values like somebody got 30% on an exam, 60%, 90%, 95%, there's a fair amount of variability. It would be nice to see most of the marks being greater than or equal to 80% in a very narrow range. But to then turn around and to have people getting 0, 5, 40, 60, 80, 90, that's a fair amount of variability in the class as well. So sometimes variability is not a good thing, but we need to be able to measure how much variability there is in the data. So there are a couple of different measures that we can use. One is called the range. So the range essentially allows us to look at the smallest value and the largest value and the distance between them. So if the lowest mark in the exam was 10, highest mark was 90, we see the range of the marks is 80, which means that there's a difference between the smallest and the largest of 80. All right? But then that could be very dangerous because sometimes there is, how you call it? You may have extreme values, and the extreme values might make it look like there's a lot of variability when in fact there is not a whole lot of variability. And so we have to then look at some of the middle numbers. So let me just switch my screen here. Back to my iPad. It would be nice if I could actually have both of them at the same time, but Zoom only allows the sharing of one item at this point. But yeah, it would be nice if I just had them in multiple windows and I could just switch back and forth between the windows without having to stop sharing one thing and then start sharing another. Might be something that I could mention to the people, you know, as a user, if that is something that they could actually do something about. All right, so the page, my iPad. So if we're looking at variability, let's just say, go back to our numbers again. 49, 52, so we had them go from 49 to 61, right? I'm going to sort of just rewrite these numbers so that nice and clean. So looking at our numbers again, 49, 52, 53, 53, 52, 53, 53, 54, 54, 54, 54. 55, 56, 58, 61. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right, so that is science and the number of hours of prep. So if we're interested now in looking at measures of variability, first one we could say is that the range. We could look at the range in the data, all right? So the range is just Largest minus the smallest. Max minus min, which case it is 61 minus 49. That gives us 12, right? So that's our range. And like I said, sometimes it's possible that we have a fair amount of, we have extreme values, but not a lot of variability in the middle. So in that case, we look at something called the interquartile range. That's where we look at the difference between the third quartile and the first quartile. So in other words, the middle 50% of the data. So which means we have to find the 75th percentile for the third quartile and the 25th percentile. So we got to take our 13 values and go 75 over 100 times 14 to get the location of the third quartile, Q3. And then Q1, we take 25 over 100 times 14. The reason why this put in 14 one time, because it is 13 plus 1 equal to 14. So that is 14 times 0.75. So that's 10.5. And the location is 14 times 0.25, a quarter of 14, 12 to 14 times 0.25, 3.5. So we need to find the value in the location 10.5 and the value in the location 3.5. Let's see. So for let's do the 3.5 first. So x at location 3.5 would be 1, 2, 3, which is basically 53, the third value. And because the fourth value is also 53, there's no space between them. So basically that first quartile is just 53. The third quartile, which is Q3, so we're looking at 10.5. Let's find the 10th value, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 as the 10th value. 0.5, 10.5 would be between 55 and 56. But because we have a 0.5, that means we need to go halfway between those two numbers. 55 and 56, halfway between that would be 55.5. All right? If you want to do the long way, you will say that's actually equal to 55 plus 0.5 times 56 minus 55. There's only a difference of 1 between those. So half of 1 is a half. And so I just add that 0.5 to the 55. And so now my interquartile range, IQR, is 55.5 minus 53, which is basically 2.5. Not a very big range in the middle. The numbers are fairly close. So there's not a lot of dispersion, there's not a lot of variability in this data. It doesn't look like it. So we have the range, we have the interquartile range with that. What are some other measures that we're looking at? So going to, we now have variance and standard deviation. Two important measures, variance and standard deviation. So let's see what those are all about. Now, because we have this problem with the range and the interquartile range as just basically picking values in the data and looking at the difference between them, we need a measure that somehow takes into consideration all of the other values in the data set. That's where we come to the interquartile, not interquartile, but variance and standard deviation. All right? So in other words, if I could take all of my values and actually find out the distance from the average. So if I could find the average of those values, and I believe the average was 54 point something, I think it was 54.38. So if I were to position 54.38, it would be between those numbers right here, 54.38. So in that case, it would be good to just kind of measure how far everything else is from the average. How far is this 54 from the average? How far is this 53 from the average? How far is this 55 from the average? The 61 and so on. So if I could get a measure of the average distance from the mean, that is a measure of variability. So that number would be large when values are fairly far away from the mean, or it'd be small when numbers are fairly small, right? In terms of the distance from the mean. So the way in which we do that is that we essentially come from a measure that we call variance. So for population, variance, V-I-R-C-E, we denote it by sigma squared. So sigma squared is we take all the x's, subtract the mean from it, we square it, and divide by n. So it's like the average of the squared distances, and we call that variance. If I take the square root of that to bring it down to order 1, I refer to that as standard deviation. Notice that my n is population n. What happens if I'm dealing with a sample? Well, we denote the sample by s squared, which is a sample. And then instead of using mu, which is the population mean, we have to use the sample mean. So to be xi minus x bar squared. Add them all up, and then divide by n minus 1 this time. Instead of n, we divide by n minus 1, and we call that variance, but sample variance. So it is similar to this one, except that instead of n, capital N, we have small n, and instead of mu, we have x bar. All right? So we call that sample variance, and the sample standard deviation is just the square root of the variance. And as you can see, we are measuring the distance from the mean. So the further we are from the mean, the bigger the value of x squared will be. The closer we are to the mean, the smaller it will be. So xi minus x bar squared, sum that, divided by n minus 1. So that is standard deviation. Standard deviation. And then this one is variance. Variance, all right? So that is the basic formula. Now, the book uses those as formulas, but I have in our formula sheet a version of that that actually makes it a little easier for you to do for calculations. So if you are looking at xi minus mu squared, it turns out that we will call this SSX, which basically means the sum of the squares, right? Sum of squares of the x's. It turns out that we could prove that this is the same as taking the x squareds minus the sum of the x, and we square the sum of the x's and divide by n. That is exactly the same value, but it's a lot easier to calculate this than to calculate that. This one you have to go and calculate the population mean, then subtract from each value, square them. This one just says, if you have the x's, add them up to give you this value, sum of the x's, and then if you take each x value and you square it and you add them up, you get this value. And it turns out that it requires a little less work than this version, but you get the same answer. So in our formula sheet, you'll notice I have sigma squared is the square root of SSX over capital N, which basically means the sum of the squares, which is, we could use this formula. And for sample, we have it as SSX, but over N minus 1, because the sample we use small n minus 1. So where this SSX is the sum of x squared minus the sum of the x's over n. Okay? So if you look at the formula sheet, you will notice that formula right there. Now, to apply it to our sample problem, let us calculate the sample. Because I'm dealing with a sample, I'm going to calculate the sample standard deviation, right? Or a variance and standard deviation. So let's do that. So for our sample problem, in terms of science teachers, it turns out that the sum of our x's is 707. Sum of the x squareds turns out to be 35,549. In case you wonder where I got that from, basically my sum of my x's would be the 49 squared plus the 52 squared plus the 61 squared. So I take each value, square it, and then add them up, and I end up getting the sum of x squareds, right? If I just add up the individual values, I would get the sum of the x's, so it's 77. So to get the variance, I would take, in this case, it's not sigma, it's s squared. It would be sum of x squared, which is 38,549, minus the sum of the x's, 707 squared, divided by the sample size. I have 13 values. So that must now be divided by n minus 1. What is n minus 1 in this case? N minus 1 is 13 minus 1, which is 12. And then that would be, I gotta just do a little quick calculation here. Equal to this value squared. Okay, so it turns out that the variance, sample variance is 8.2564. When you compute that, which means the standard deviation, S, is the square root of the variance, which is the square root of x squared, would be the square root of 8.2564, which turns out to be 2.873. 2.873, something like that. Okay? So that's the standard deviation. That's the variance. One is just the square of the other. What does this measure for us? As I mentioned to you, it measures the average distance. In other words, if I use the standard deviation, not the variance now, because the variance is a square, but if I use the standard deviation, it measures for us that average distance between the numbers in the distribution and the sample mean. Because remember, the numbers will vary around the mean. So the further they are away, the more variation there is. The closer they are to the mean, less variation there is. And so S, or S squared, measures for us that distance. Okay? So I've just calculated variance. I've just calculated standard deviation. There is another important measure, which is called the coefficient of variation. Now, the coefficient of variation is a relative measure. It is a measure that allows us to express the standard deviation as a fraction of the mean. All right? As a fraction of the mean. So let's take a look. So coefficient of variation is a relative measure we use CV to represent it. So CV for population is sigma over mu, if we had the population. But for sample, so that's population, for sample, CV is equal to S, which is sample standard deviation, over X bar, which is sample mean. All right? So for our example right now, we had a sample mean of X bar for science was 54.38, and S was 2.873, I believe. So therefore, our coefficient of variation is 2.873 divided by 54.38, whatever that turns out to be. That is your coefficient of variation. Let me see if I can compute that quickly for you. I'm not seeing my sample problem I had here. Okay, I see it now. So here's my mean and my standard deviation. It turns out that that is divided by 54.38 is 0.0528. 0.0528, we can actually express it as a percentage, which basically means the percentage of the mean that the standard deviation represents, which is essentially, in this case, 5.28%. And that is actually quite low. What does that tell us? It means that the teachers are spending, all of them are spending approximately the same amount of time. If there was a lot of variability, it means that some teachers are spending a little bit of time, some teachers are spending a lot of time. But because there is not a lot of variability between those two, between the values, that's why we have such a low coefficient of variation. Normal coefficient of variation is about 20%, 25%. And then if you start getting 30, 40, 50%, then that's a fair amount of variability. But to be down to 5.28%, that's actually pretty good. So that means that for this data set, which varies between 49 and 61, most of the teachers are spending approximately the same amount of time, 54.38 hours per week to prepare for classes. All right? Good. And that's coefficient of variation. Let's go back to our PowerPoint for a second. Let me see if there are any questions. Okay, I see a chat here. All right, Kylie, no problem. Let us go back to, we're almost done the lecture for tonight. We want to. So we've talked about range, interquartile range, variance, standard deviation, and coefficient of variation. So in essence, we've covered all the examples that we have here. Let's take a look. So this data set with the rents is still being used as an example. So the range, if you arrange the data in ascending order, you see your minimum is 525, your maximum is 715. The difference between them is 190. So the range between the smallest and the largest is $190, right? That's an example right there. Interquartile range is the range in the middle, 50%. It overcomes the extreme data, so we first have to find Q3 and Q1. We know how to find those. When we compute that, it is 625 minus 545, and that is equal to 80. So in the middle 50%, the distance between the range and the third quartile and the first quartile is $80 between those. Variance is a measure of variability that utilizes all the data. It is based on the difference between the value of each observation and the mean. So kind of like spread around the mean is what it does. And you see that formula I gave you for sample, formula for population, and what happened is that I give you a shortcut formula that the book does not give you. I want you to focus on using the formula I give you because it's less work. So standard deviation data set is positive square root, which basically is just taking the square root of the variance. No big deal there. And the coefficient of variation allows us to express the standard deviation as a fraction of the mean. All right. And then we see some sample calculations right here. Now, there are two other things that I want to discuss with you. Let me just double check that I'm not moving too far ahead of our course outline. Give me 1 second. Just taking a quick look to see where we're supposed to arrive today. Okay, so we do have to do section 3.3. Yes, we do have to do 3.3, which basically talks about z-scores and covariance. And I do have videos that were actually created for that. So let's talk a bit about z-scores, covariance, and the empirical rule. So those three parts right here. Let's talk a little bit about that. So first thing we're going to talk about is, so now we start to get a little bit into what we call the shape of the distribution. So first we start in terms of measures of location. Then we talk about the dispersion of the spread in the distribution. Now we want to get into the shape of the distribution. We're still dealing with one variable, so let's, in terms of the shape, let's talk about something called a z-score. So a z-score is basically a way of expressing the difference between the average and values in the distribution, but in standard deviations. It's kind of like how we might take, say, distance and measure it in feet or inches. Well, in this case, we want to measure the distance between an observation in the distribution and the average according to in standard deviations. So let's just say if this were our x bar, for example, and we have x1 here, x2, x3. It's not x bar 3, sorry, just x3. x4. So these are values in our distribution. I could try to just measure the distance here between those numbers. But what if we're talking about, what if our numbers are in thousands of dollars? Then we just have a big, large number. What if our numbers are in, say, degrees, terms Celsius? You know, we just have a set of numbers. What if our numbers represent cubic feet? You know, and so if you want to get away from that, it would be good to standardize the measure, actually express it in a value that has no units at all. So if there's a way for me to express that distance or express this distance, that would be great. Well, we do that with what we call a z-score by taking the x value, subtracting the average from it, and dividing by the standard deviation, and that is a z-score. It measures the distance between the values in standard deviations. If it's for population, it would be x minus mu over sigma. And that's for population, and that's for sample.
Excuse me, Dr. Miller, are you supposed to share a screen with us there?
Sorry?
Are you supposed to be sharing a screen with us?
Ah, I'm sharing. Okay, so I'm still showing the PowerPoint, am I?
Yeah.
Okay. Yeah, that's where I really wish we had the we had multiple screens up on the same and just flipping back and forth. I have to literally stop sharing what I'm sharing now and go back and share the new one. Okay, so there we go. Thank you for that. So if you look now, so what I was trying to show is that if this is my mean right here, my sample mean, it would be nice to be able to measure the distance between those. But if I just measure them in the units, sometimes the units are very large, sometimes they're very small. it would be useful if we could actually express them in a unitless fashion. It's kind of like how when we put two numbers one on top of the other, if they happen to have the same units, we could express it as a percentage, and the percentage has no units as such. The percent, so in that case, we get rid of the units. In this case here, we could get rid of units if we take the distance between the two numbers and then we divide it by the standard deviation, because the standard deviation has the same units as these values right here. So by taking x minus x bar and divided by s, we actually are saying there's a distance between x and x bar in x number, however many standard deviations that turn out to be, and in this one as well. Now, one of the useful things about that is that depending on how many standard deviations the values are from the mean, we can know if those numbers are outliers. So if it turns out that the rule is that if the Z score is 3 or higher, either -3 or lower, or 3 or higher, in other words, the distance is more than 3 standard deviations, you consider that an outlier, all right? Because that's considered very far. 3 standard deviations away is considered very far. And you will appreciate that a little later when we do the normal distribution, all right? So for now, or the bell curve, some of you might be familiar with the bell curve. So, but for now, we're just measuring the distances, and those distances, if they're larger than 3 standard deviations away, whether it's on the negative side or the positive side, we say that is an outlier. So that's helping us a little bit with looking at the shape of that distribution and so forth, all right? So that's the Z scores. And we could actually take the examples that we did, because I think we found in the example that we did, we have our S was 2.873, I believe. Our X bar was 54.38. So I could actually take all of the values. For example, I had a 41, I believe it was. So 41 minus 54.38 divided by 2.873. That's a Z score right there, all right? How many standard deviations is that away? Let me see if I can calculate that actual value and tell you if it's an outlier. So that is 41 minus 54.38. I'm using Excel to calculate that right now, divided by 2.873. It turns out it's negative 4.65. That is indeed an outlier. So whoever, oh, it was 49, I said 41, so there's no wonder it's an outlier. If somebody, let's leave it as it is. If somebody spent 41 hours, preparing for the week, while on average people are spending 54.38 hours, I'm sure that you would appreciate then that person kind of spent a lot less than the other people. So that is why statistically it's considered an outlier. But it was actually 49. If I correct that value, and I could do that very quickly since I did in Excel, let me see if 49 is still an outlier. Nope, 49, when I use 49, it turns out to be negative 1.87. So if I do that, then in that case, it's not an outlier. $49, maybe 1.87. So that's a lot smaller than 3 standard deviations. So that 49 is not an outlier. So we can't say, hey, this person is lazy because they spend a whole lot less than the rest of the group, because it's not an outlier, okay? So that's with the Z score. Now, what is the empirical rule? The empirical rule allows us to take advantage of these Z scores to say something about the shape of the distribution. What happens is that in statistics, we are quite interested in whether or not our distribution has a bell-shaped curve. Everybody's familiar with the bell-shaped curve, right? It's nice, it's symmetrical, it has a mean mu, standard deviation sigma, and it's nice and symmetrical. And the reason why we're interested in that is because there's so many distributions in real life that actually looks like that. So for example, if we look at an organization, we might say there are a few people making a lot of money, a few people making very little bit of money, and most people are somewhere in the middle. You can find a lot of distributions like that. We refer to that as the bell-shaped curve or the normal curve. Normal distribution. We'll talk about that some more in chapter 6, normal distribution. And with this distribution, it turns out that if we have our sample coming from that shape of a population, if we calculate Z scores, or if we calculate X bar and S, there's a particular rule that applies. And here's the rule. The rule says we don't know what the population mean is or the population standard deviation, so we will use the sample values that we have. If I were to take the sample mean and I added and subtracted one standard deviation to it, and then I calculated that range, so basically I would get X bar minus S to X bar plus S. If the data came from this bell-shaped curve, which is the population, when I count how many values in my sample are in that range, that should be approximately 68% of that sample should be in that range, within one standard deviation of the mean. If I now go to 2 standard deviations, so I'm making the interval larger, X bar plus or minus 2S, which case I'll calculate X bar minus 2S to X bar plus 2S, then it turns out that that is 95%. So if I count how many values in the data is in that range between those values, inclusive, then about 95% of the values will fall in that range. And then if I take 3 standard deviations, so in other words, X bar minus 3S to X bar plus 3S, we should get 99.74. Almost all of the data in our sample should be in that range, if the data came from a bell-shaped curve. All right? That's called empirical rule. Now you might say, well, yeah, but why is that important? The reason why it's important is because that distribution, that shape is very important in statistics. And if we could ever get enough of the, evidence that our population is shaped like this, then we are able to utilize the conclusion that the population is a bell-shaped curve to our advantage. So the reason why we want to be able to test a distribution to see if it conforms to this pattern is because if it does, we could do a lot of things with the assumption that the population is a normal distribution. And that will become clearer as we go through the course. At this point, it's early, but then it will become a lot clearer. All right? So that is the empirical rule. So literally what you have to end up doing is to go and take the sample mean, sample standard deviation, calculate those 3 ranges, count how many values, literally count and say, oh, this value is in the range, this value is in the range, this value is in the range. You count them, and then you divide that by the total number of the sample size, and then you get the percentage of the sample size. So if say for example I had these I had 70 values, and in the data that we used in the rents, in the 70 rents, and then I calculated the range of for one standard deviation and found say 35 of those were in the range, then the percentage that's in that range is 35 over 70, which is 50%. Now that 50% does not look like 68%. There's a big difference between that 50% and 68%. So the idea being we could actually do an empirical test to determine if the population might actually be a bell-shaped curve. All right, let's take a look at the rest of that chapter through the PowerPoint notes, right? And then we will shut down shortly. So we did talk about z-scores. I just mentioned the idea of z-scores to you. There's Chebyshev's theorem, which we don't have to know as such, the empirical rule, and detecting outliers. I've already talked about the empirical rule, z-score, and outliers are when we have values of 3 or higher, then you have outliers, right? The shape of a distribution, which is skewness, we'll pass on that for now. And it just tells us whether our distribution is right skewed, left skewed, or symmetrical. And we will skip that. Here's our z-score, xi minus x bar over s. It's called a standardized value. And it basically tells you how many standard deviations from the mean an observation is. And you see a calculation right here. In fact, it was calculated for all of the values for the rents, and none of them are actually greater than 3. So therefore, none of those values are outliers. Now, I talked about the empirical rule in terms of within one standard deviation, you have 68%, within 2 standard deviations, 95%, 3 standard deviations, 99%. Chebyshev's theorem gives us a range that says at least 1 minus 1 over z squared of the data values must be within z standard deviation. So if we say, for example, 1 standard deviation, so within 1 standard deviation of the mean, at least 1 minus 1 over 1 squared. Well, that doesn't tell us a whole lot. For any value that is greater than 1, so I guess we'll have to use, like, let's say 2 standard deviations. So it's 2 standard deviations. If we put 1 minus 1 over 2 squared is 4, that's a quarter. 1 minus a quarter is 3/4, so it will be at least 3/4 of the values will be within 2 standard deviations. And you can calculate it for 3 standard deviations. 3 3s are 9, 1 9, so therefore 8 9s. So at least 8 9s of the data will be within 3 standard deviations and so on. So that's just a theorem called Chebyshev's theorem, which we don't really have to know a whole lot. So you guys can see it's being calculated there. And they test it. The empirical rule, which I've done with you, here says approximately 68% of the data will be within 1 standard deviation, 95 within 2, and almost all of it within 3. So you see the bell-shaped curve within 1 standard deviation, then 2 standard deviations, 95.44, 99.72, within 3 standard deviations, and so on. Detecting outliers, when the score is -3 or greater than +3, we have an outlier, right? And it might be that the data is incorrectly recorded, data was incorrectly included in the data set, correctly recorded data that belongs in the data set, but it just happens to be an outlier. Okay? And we see it being applied to the data that we have. All right? There is something called 5-number summary, which we actually skip, so we're not covering 5-number summary. So we'll skip that, which is basically a way of looking at the data, called box plots. So we're going to skip box plots for now. The only thing that's missing is the very last thing, which actually is a little challenging to get at this point, is the idea of association between 2 variables. I'll just discuss this briefly and let you go through the example that I have in the video lectures. So in this case, we're now moving away from one variable to two variables. And this is when we want to look at how can we measure the association between two variables if they are negatively related or positively related. So for example, interest rates and say loans. A bank wants to know if there's some kind of relationship between the interest rate is charging clients and the number of loans that is actually selling. So obviously when the interest rate is high, the number of loans that it will sell will be lower. When the interest rate is lower, the number of loans that it will sell will be higher. So those two variables, interest rates and number of loans sold at a bank, would basically be negatively correlated. That means when one goes up, the other one goes down and vice versa. And there's a way to actually compute that. So we call that covariance, and covariance, unlike say regular variance, can be negative. So if there's a negative relationship between the two variables, your covariance will be negative. So in essence, this measure tells us how the two variables vary together. So if one goes up, the other one's going down. If one goes down, the other one is going up, and so forth. So positive values indicate a positive relationship. Negative values indicate an inverse relationship between the two of them. All right. And here's the formulas that you would use. So if you were doing covariance, so now what you do is you're taking the mean of the x values and subtracting the means from it, and taking the corresponding y value and subtracting the mean from it. Adding those up and then dividing by n, and minus 1 will give you the sample covariance. And then if you did it for this right here, you get the population covariance. Notice that this is now n, but it's the same idea. Instead of x bar, we use mu. Instead of y bar over here, we use mu y. So we have the two variables because we are looking at the relationship between two variables that are associated, and we call one x, we call one y. And typically one is dependent on the other. So the one that's dependent we call the y, the one that's independent the x. So for example, the number of loans that are processed will be dependent on the interest rate. So we'll call number of loans y and the interest rate x. X is the independent variable, y is the dependent variable. And so through this process here, we can actually compute the covariance between two variables. And when that covariance is positive, that means that they both move in the same direction. When they're negative, they actually move in opposite directions. Now, while the book uses those formulas, I want to give you the shortcut formula because I do have the shortcut formula in there. So let me just switch over very quickly so that you can see the shortcut formula. So the shortcut formula for covariance of x and y. X is independent, y is dependent. All right? And so cos x, y is essentially what we call SSXY over n minus 1 if it is sample, or SSXY over capital N if it's population. So population, this here is sample. And then the shortcut formula for SSXY is the sum of x times y minus the sum of x times the sum of y over n. it kind of looks similar to this. Sum of x squared minus the sum of x all squared over n for SSX. Except that instead of dealing with SSX, we are dealing with SSXY. So this represents x times x, but here this represents x times y. In this section right here, this represents sum of x times sum of x, whereas over here, it would be sum of x times sum of y, right? So as you can see, they're similar, but because we're dealing with two variables, x and y, we have to modify that slightly. And that's our shortcut formula. If you use that, it actually takes a little less work than if you're using the other formula that I showed you here, all right? Which is the one that the book uses, the one that I showed you in the PowerPoint slides. So I would like you to use that as the formula for calculating covariance, all right? So if you could do that, that would certainly save you some time. And I believe, last but not least, is a measure called the correlation coefficient. Now, we're bringing it up a little bit early here, but we're coming to it at the very end of the course. We'll be coming back to this exact same measure. So now when we believe that they have this relationship between those two variables, we want to measure the strength of that relationship. So we use something called the correlation coefficient. Okay? So correlation coefficient. If it is population, we call it rho, R-H-O, for population. And then we use R for sample. And it's calculated as follows. Now, the book gives you the following formula for samples and populations. For samples, it will give you RXY is equal to SXY over SX times SY, where essentially this SX and SY are standard deviations. Standard deviations. Standard deviation of X, standard deviation of Y, and this part on the top right here is actually the covariance of X and Y. So covariance X, Y. If we are dealing with population now, we'll just simply switch it to rho XY. We switch to sigma XY, sigma X, sigma Y. And that will be for population. Again, instead of sample standard deviation, we'll just have population standard deviations and the population covariance. I don't really like this way of presenting it because I find it confuses me a little bit that one is a covariance at the order level 2, and then the denominators are standard deviations at order level 1. But instead, without going through the proof for you tonight, we could actually write this as follows. R, or rho, is SSXY that I showed you early on, divided by the square root of SSX times SSY. I'm not talking about SX, which is the standard deviation. I'm talking about the sum of squares X, sum of squares Y. And you may recall earlier I told you that we have the shortcut formulas. This part right here would be sum of X times Y, sum of X, sum of Y over N. That would be that numerator right here. This one would be sum of X squared, sum of X all squared over N. And then this one would be sum of Y squared, sum of Y squared over N. And that's what this one would be. So if we use these formulas right here, that's your SSXY, your SSY, and then your SSX, you get exactly the same answer, but I find it less confusing than this stuff right here. So I would recommend that we use that for correlation coefficient. Correlation coefficient turns out that when we compute the values, whether it is rho or R, sorry, that's not rho, that's R. So rho or R varies between -1 and +1. When the value is -1, it's perfectly correlated, but it's negative. +1, perfectly correlated, but it's positive. So in this case, we would have a totally, so that's Y and that's X. All the points would be on the line. In this case, that's Y, that's X. All the points would be on the line, right? But in between, you'd have something like, you could either have something like this, or you could have something like this. It all depends, right? And so the closer you are to the 0, then the less amount of strength you have in terms of a relationship. But the closer you are to -1 or +1, the stronger the relationship. All right. So that's our pretty much our review here for that section. Right. Let me just see here. Go back to. Okay. And so we see here correlation coefficient values between -1 and +1. And sorry, if I go back, we have strong negative relationship, strong positive relationship. Closer to 0, the weaker the relationship. And here's an example where these two, the average driving distance and the average 18-hole score. And we see here, is there a correlation between the average driving distance that a golfer hits and the score on an 18-hole golf course? And all of the values are computed. You have the sum of the X's, the Y's, but then the way the book does it is by using this formula right here. In that case, you would have had to go on and find X squared, Y squared, and then X times Y to compute the values that I showed you in those formulas. All right. That brings us to the end of that section on correlation coefficient. So we've covered, let's stop the share. So we've covered pretty much all the topics that we want to cover in chapter 3. I have the videos right there, and then there's also some sample problems that are worked in MindTap that you could actually utilize as additional examples of each of those things. So use MindTap to show you the rudiments. Use the videos that I have to give you a review of sort of a revision of the topic, and then do some practice problems in terms of MindTap. I think gives you a couple of them for you to practice. You could certainly try those out, make sure that you understand it. Now you have an assignment that's due this weekend. I'm going to make it this very first assignment. I'm going to give a little extra time on that one. A student contacted me about that, and I will probably make it due the Tuesday night before the class next week. So in that case, you'll have a couple extra days to do it, because apparently there's still some confusion. Some people thought the class was at 6:30. Some people thought it was on Monday, and so forth. But anyway, you are able to now, I will change the due date of the first assignment so that you actually have until Tuesday to complete it. All right? Good. So hopefully that was useful in terms of the review and going over measures of location, measures of variation, and measures of association, in this case when we have two variables. And that covers chapter 3 for us. If there are any questions before I say good night to you. If anybody has any questions, then we could certainly look at that. Just checking chat room. Nope, a couple of folks had to leave. So thank you very much for attending, guys. You know, if you need to make an appointment to talk to me, send me an email, and then we could try to schedule a Zoom appointment. I'm not in office, so you can't drop by SMU and find me. But certainly, if you know there are specific questions that you want to ask, we could do it just before the class time or just after the class time, or we could schedule an appointment via Zoom. And as I mentioned in my email, I could make Zoom private so that only one-on-one conversations will happen as opposed to multiple people. All right? So on that note, if there are no questions, thank you very much, and good luck with the first assignment. Okay? So I'll see you then next week, God willing. Take care.